Okay, I think we should be good to go. All right, well, thanks for joining, everyone. Just give a quick intro here on what we're planning on covering today. So, start with just an overview of Qube, our company, and a bit of a basic understanding of how our technology works. This type of continuous monitoring technology is still fairly new to the RNG space, so I want to make sure we give a bit of an overview there. And then I'll talk a little bit about the farm RNG market and what makes it unique and why leak detection is so important. I should note the policy regulatory aspect of this is going to be focused on the US, but I do think from an operational standpoint, this really is applicable just about anywhere. And then I'll try not to spend too much time on talking about us and Qube because I think the most exciting thing, at least in my mind, is being able to share some of the data from the field. So a case study and just some of the different insights we've gathered along the way. Sorry, PowerPoint was freezing for a second there. Okay, just an intro about Qube. So we started commercial sales in late 2020. We have two offices in Calgary, Canada, is where we originally started out, and then we also have an office in Houston, in Texas, where my colleagues Braxton and Kathy are joining us from today. Since 2020, we've sold and deployed over 5,000 devices. We are getting close to 6,000, so we're almost able to change this number on the slide. I should note about 90 or a little over 90% of those devices have been in the traditional oil and gas market, upstream and midstream production. And then beyond that, the biggest kind of other market has been farm RNG. We've also deployed at lots of other types of industries like landfills or coal mines. And then the only thing, other thing I'll give a shout out here is just some of the folks who've had the opportunity to work with and are really thankful for, and particularly for this call of Roeslein Alternative Energy. They were our first partner in the farm RNG space, and they actually were kind enough to give us permission to share one of the case studies from our work with them. So we really appreciate that. Okay. In terms of the technology itself, we typically think of continuous monitoring as having three different components. So there's the physical hardware, and that's an array of devices that are collecting raw data on a continuous level. Every 3 to 5 seconds, we're taking measurements on things like the wind speed and the direction. Each device has a gas sensor, so it's giving you the parts per million of methane in the atmosphere. We also can add additional gases from relevance for an RNG standpoint, gases like H2S or NO2 or SO2 to help with odor management. Now, all that raw data from each device is then sent into an analytics platform because each device is connected to the cloud, whether it's through a cellular LTE connection or Wi-Fi. And then that data gets sent to the cloud and it's processed by our air dispersion model. And so that allows us to, when these devices are detecting methane, if it's a large enough detection, we can then give an estimated size of the emission event, like how much is it leaking on a per hour basis, and how long is that going on as well. The last part of this is the dashboard. So that's what customers end up seeing. And so for that example of a detected emission, customers can set a threshold for an alarm alert. And so based on when they want to be notified in terms of how big the leak is or how long it goes on for, they then get an automated email that says, hey, we detected a leak. It's coming from this location. It's this large. And then they can actually go out, verify that, and fix it. The dashboard also has lots of other tools, be able to see your emission trends over time, seeing a heat map of your site and where emissions are coming from. And I'll let Kathy talk more about that in a couple slides here. So the last thing on the specific hardware and technology, I just want to point out that these devices are made to be very resilient across a wide range of weather locations or weather conditions. Hopefully, none of you folks are operating below -40 or above plus 140, but at least in between there, we have the ability to deploy our devices. These devices are solar powered and they can last over 7.5 days without sun. Just for context, we're a Canadian-based company originally. We've deployed these devices in the winter in northern Canada where there really isn't a whole lot of sunlight. In fact, out my window right now, it is currently snowing and we haven't had issues there. So that's been a good kind of proof point and test for our devices. These devices do each have an anemometer. So that's able to record the wind speed and direction continuously. Usually they get mounted to a post or a fence line, but if needed, we can also mount them to a tripod stand. As I said, they are pretty resilient, and that's certainly how they're designed. But if maintenance is ever needed, these devices are also modular. So any component, whether it's the anemometer, the solar panel, or the gas sensor, can be swapped out pretty easily without needing to take the whole thing apart or take it off of the mount. Now, just on the right-hand side here, just have an example what this looks like in the field. And so this is a covered lagoon digester for an example. And depending on the size of the lagoon, we'll usually deploy around 4 to 8 and maybe more if it's a really large lagoon. And the device count does depend on that size, but also can depend on offsite sources. So typically we deploy these devices in array downwind of the lagoon so that as if there's a gas leak, that gas is transported to our devices and then that inverse air dispersion model I mentioned then can calculate and see where the leak is. But if there are offsite sources, for example, if you have an open lagoon upwind of your covered digester, or maybe you have barns, and those are still releasing methane gas that's then being transported across the lagoon to our devices. We then can put devices in between on that upwind side so that the model filters out that offset contributions. So we're not giving you what we'd call a false positive to say, hey, there's gas detected from this lagoon when really it's being carried over by the wind. And with that, I'll turn it over to my colleague, Kathy.
Thanks, Jared. I'm Kathleen Jenkins. I'm a customer success manager here at Qube. So what I do is work with the customers and the clients after they have had devices deployed. So part of my job is to train them on understanding what the dashboard is. In this situation, we landed in the overview page for an organization, and it gives the asset level summary. There's the map, and each black dot is a site, and the green bubble gives the relative emission volumes compared to the other sites over the time period. The time period is actually seen on the upper right-hand corner, and you can select custom periods or time frames like 12, 24 hours, 30 days, or your own variety of them. When you look at this, you can also see the trends basically over the last 2.5 months or 3 months, depending on how close we are at the end of the month, over the volumes and alerts count of all the sites under this organization as well as an overall average site rate. So you can see how you're trending. And then on the next one, you could see it's ranking the sites by the volume, the alert count, and the average daily rate. So that's giving you a bigger picture and then getting more minute information. You see what kind of equipment on the site. This is an oil gas site. So you see there's tanks and separators on this. So you could start seeing which type of equipment causes most of your emission events. So if you click on a site, then you see the site page, you see an image and you see this covered lagoon site and you see the lagoon there and you see the barns. You'll see the boxes with the colors and the white numbers on them. Those are the devices, locations, and the numbers around the site. We use a satellite image to get a better picture. And so that way you can see where the devices are in the scheme of things. The wind rose, you can click a button and see the wind rose shows the direction the wind has been coming to the device when it detects methane. So you see we have some devices in between the barn and the lagoon so you can see which direction the emission is coming from. And over time, you can see for the time period, you can see which source on the site has received or highlighted as given most of the emissions. And the emissions timeline actually identifies when the on-site emissions occur. Like we said before, the devices are always reading. Yeah. Given that there's anemometers on each device, it actually filters out and only calculates the emissions for when the wind is coming from the site itself. So it gives you the bring over, it gives it details, the location, the rate, the volume, and the duration of the event. And you can see as the instant rate or the rolling averages. You can actually see hourly or the rate over time averaging up to 90 days. And we said before, you can see the concentration at each device. So that way you can see the important details, but really we focus more on the rate because we want to filter out the offsite emissions. We know that it's important to see the ppm, but you don't want to rely too much on that given that there's offsite emissions at most of these facilities.
Okay, thanks, Kathy. Yeah, and maybe one other thing to mention too, and simply because we didn't have room on the slide, but you can also see other types of device level data if you really want to dive into the weeds. You can see the wind speed for each device. You can see the wind direction as well if you really want to investigate what's going on. Okay, so on to the next section here. So I should acknowledge, I'm not entirely sure the composition of folks on this call and your level of familiarity with farm RNG and policy. And so there's a good chance this slide is very redundant and obvious, but I know a lot of these things for me certainly weren't obvious when I started. So I want to give a bit of an overview just to set the stage of what makes this farm RNG market unique and then also what drives this high price premium we see. So there are programs that incentivize RNG use in the states. The two I wanted to call out are you have state-based programs, primarily called low carbon fuel standards, so LCFS for short. The main one is in California, but there are a few other states that are in the process of implementing a program like this, and then quite a few other states that are actively considering implementing one. Something that makes LCFS unique is that the number of LCFS credits you get for each volume of RNG produced is based on the carbon intensity of that specific pathway and that specific project. And so because of that, the livestock manure, so farm RNG, has the lowest carbon intensity score out of any other RNG source. And this is due to avoided emissions, which is that in a baseline scenario, we're not covering this manure and capturing the gas. It's assumed that it's being, let's say, spread on the fields as fertilizer, and all that methane is going into the atmosphere. So that gives you a very low carbon and actually extremely negative carbon intensity score, which generates a lot of credits for this particular source. The other program to note is the federal program, Renewable Fuel Standards. These credits are called RINs for Renewable Identification Numbers. And it's a little bit different than the California program because they're not project specific, but they're placed in broad categories. That being said, farm-based or manure-based RNG is still placed into a category of credits that's more valuable than other sources of RNG, like food waste. And so you can stack these two credits together. You don't have to choose one or the other when you're producing gas. You can get revenue and credits from both. The other thing to note is even though LCFS is a state-based program, you don't actually need to be in that state. Let's say California in this example, producing your RNG gas in that state to benefit from the program. There's something called the book and claim system, which essentially means you could be producing RNG from a farm in Missouri. If you find a customer that wants to buy that gas and get that credit in California, you just need to inject the gas into the grid in your local grid, say in Missouri, and that customer then takes gas from the grid in California, and that's considered a transaction. Even though it's a state-based program, it really does influence the entire country. When you add these two programs together, what you end up with is a significant price premium, and that's really driven by that low carbon intensity score due to avoided emissions. When I looked up before this call, the latest prices I could see were around $65 per considered typical CI score for farm-based RNG. And this is a lot higher, 25 times higher than typical conventional and wholesale natural gas. And even I wanted to note, LCFS credit prices are actually quite low right now. In the past 3 to 4 years, they've actually been 2 to 3 times higher than this. So this price of $65 per MMBTU can actually be a lot higher. And so the key point here, and something we want to talk more about in the rest of the presentation, is when you have gas that has this much of a price premium, any leak you have is very expensive in terms of lost revenue. Okay, so let's talk about leaks. So this is just from an academic perspective. We'll get into our own data after this. We wanted to show there's a couple of studies that have come out where they've surveyed a wide variety of biogas RNG plants. And the one on the left found an average leak rate of 4.8% of total gas production volume they were losing due to leaks. And then the one on the right was 2.4% for agricultural biogas plants specifically. I know I just picked a couple of scientific studies. I'm sure folks have seen a lot of inflammatory type articles about this as well. And one thing to note as well is this research has focused on digesters that are upright. They have concrete walls, membrane domes. You might hear them referred to as continuously stirred tank reactors or a complete mixed digester. What's interesting is even though the research has shown they do leak quite a bit, most kind of research or the California LCFS model actually assumes that covered lagoons, which is where we've done work so far, is actually even higher than these CSDR type digesters. And I think one thing that I really want to emphasize, and then we'll talk a little bit more about on the next couple of slides, is these leaks, these averages they're not inevitable. They're not like an inherent flaw in the design of these digesters. They can be caught, they can be fixed. And I think that's something that's missing typically from public discourse, especially this type of inflammatory articles is they take studies like this and they extrapolate and they say, because of this, then these RNG operations are bad. And I think what we've seen so far in our work is that's just not the case, and that these can be low leak and low emissions. Okay. All right. Back over to Kathy here.
I was just saying that the important thing is keeping the revenue system coming, the revenue flow going. And this was a situation where I had an odd situation occurred. There was a storm that caused a major tear in the lagoon cover. And you can see if you're looking down below the image on the left-hand side, the emission alarm was triggered and it sent an automatic alert to the operator. And they went on site. So you can see where the emission ended when they repaired the leak. But the whole thing is that this was a one-off situation. There was the sensors there. You could see the plume that was floating across and how it hit the different devices. And you look over to the right, there's the scale, the gradient, its ppm is seen there. And then you could see how it reduced as it flowed over. But basically the whole issue is that there was a large emission, 658 MMBTU per day, was caught. The operator went and repaired it. So that way they kept their revenue flow going where it needed to go instead of going out in the atmosphere.
Yeah, absolutely. I think it's hard to project forward how long this leak might have gone on if there wasn't some sort of leak detection. But I think you can imagine a leak that's producing, over 600 MMBTU a day that's leaking to the atmosphere, and this revenue is not going to the pipe. If that carried on for a week or 2 weeks, that's a lot. You saw the price on the last slide of $65 per MMBTU. If you're leaking over 600 a day, that's a pretty big impact there. And one thing I just wanted to note too is I was looking at the data on this one just yesterday because I knew we had heard about this being a major storm. So I was imagining there's some crazy wind that's just causing massive tears everywhere. The storm is actually only 10 to 15 miles an hour wind, which is, to be fair, it's high, but it just shows that these types of leaks can occur even in relatively normal conditions.
One thing that we've seen from all the sites is that most of the emissions come from the anchor trenches around the lagoon. Looking One of the things that we can do with our dashboard is you can export the information and start data mining it and tweaking with it a bit. The wet wells have a lesser account are the sources. The covers, as much as they are the whole site, it's actually only 29%. But the anchor trenches, basically on whole, is where most of the emissions have come from. And over in this bar graph, that's 100% of the emissions for the different site. You can see that each location has its own type of emissions, our own sources where they come from most, and it's often based on what the lagoon or the facility is used for. Some of the facilities are holding pens or holding facilities for emissions to come through before they're sent out through the pipeline. So maybe there's more emissions from the wetlands, things are sent through. But the fact is that you can catch these emissions, and most of them you can take care of right away.
Awesome. Thanks, Kathy. Okay, as Kathy mentioned on the right-hand side, that's essentially a sample of a number of sites we've worked on across different operators. And so I wanted to look at those sites and then look at how much are they emitting per month on average. And this is just what we'd consider the production season outside of California, where Central Valley, it is quite warm for most of the year. But in other areas of the country, you're really only producing this gas during the warmer months. So we looked at May to September. And what this shows is for all those sites, ordered them from highest to lowest in terms of the average monthly emissions per site. And so there certainly are a lot of factors that can determine how much each site is leaking. And of course, the size of the site and volume of gas or volume of manure in the lagoon is a very big factor. But a lot of these sites that you see are actually similar sizes. And still you see different leak rates. And so they're similar sizes, they're made with the same materials. You see a wide variation in leak rates. I think one other thing to point out too, the gray bars here are the average monthly emissions. The red dashed line, that's the max emissions over the time period we've worked on these sites that you've seen. So I think one thing to highlight there is it's not just that this site, for whatever reason, is a leaky site and it's always leaky, or this site is a low emission site and it's always low. You still see this high variability where any of these sites, even if they traditionally have a lower leak rate, they can have a spike. They can have a single leak, whether it's caused by a storm or an imperfect seal along the anchor trench or an issue with the weld on the web, they can still have an intermittent leak. So that kind of goes back to the point a few slides ago about with these studies that have estimated leak rates, it's assumed to just be this constant thing across sites. And again, that's just not what we've seen. But that being said, given that these low emitting or lower emitting sites can have these big spike events, I think that does reinforce the importance of catching those leaks when they happen. I think if you aren't catching the leaks and repairing them, you'd see the average of these sites be a lot closer to the max because that single leak event would continue on over time. Okay, so the last kind of data specific slide we wanted to show is now that we've been at some sites for over a year, we wanted to look at a comparison of essentially when we started monitoring those sites and then now. And so we have data from 2023 and 2024 for the months of July and August because we started one of these in July. And I want to note as well, the data for 2023 we were in the process of getting started. We're deploying the devices, training the operators on the dashboard. So there was some use of the devices at this time. And so I actually think the 2023 data actually could be higher if they weren't doing some leak detection or repair with the devices at the time. But what we've seen then is over those months and over the winter, as all operators got to speed on using the dashboard, we had all the emission alert alarm threshold set. Now we came back through and had a full summer season with these devices operational, we saw a pretty dramatic drop of around 40%. And this is across a wide group of sites. So this is an average. So some, of course, had a higher drop in emissions, some had lower. There's a pretty big sample set to be able to show, I think, what the impact of doing leak detection on a regular basis can have. And again, just to call it back to the revenue aspect of when you have these really high gas prices, or let's say over $65 per MMBTU, that reduction in monthly emissions is a lot of money. All right, so we're just about ready to wrap up here. So maybe I'll just kind of one slide to conclude and highlight some of the key points we wanted to get across. So the first one we've talked a lot about already. So the idea of leak detection being a source of revenue, not just a source of reducing costs or reducing risk, but really being able to maximize revenue, which is the main focus of this webinar today. But the next couple we didn't talk a lot about. I think one of them is just saving time. And so when we talk to operators about their leak detection practices, certainly every operator does it differently. But the one common thread is that they end up spending a lot of time walking and trying to find like leaks on their own. So whether it's walking around the cover, on the cover, and if you can imagine the lagoon cover, so you've got this black tarp trying to find a tiny little leak on that black tarp with black manure underneath it, or even if it's like a CSDR upright standing dome, how you find a tiny pinhole leak in a dome that's maybe 40 or 50 feet high. And so by having continuous monitoring, you're able to do what we'd call do a survey by exception. You're only going necessarily to go and inspect leaks when we've alerted you to there being a leak in this area, and you're not sending someone every day or every 3 days to do that kind of time consuming, arduous, and difficult to spot walk. And then the last thing, I talked a little bit about this earlier, but even though methane is our main focus and it's what our model for the air dispersion model is based on for localizing and quantifying leaks, each device can also add up to 4 other gas sensors. And so things like H2S, NO2, NH3, we're working on that right now. We're just finalizing that ammonia sensor. But because each device has an anemometer to have wind speed and direction, you can tell whenever there is a detection of these odor causing gases, where is that coming from? Whether it's on your site and you can have a better idea of how to manage that odor, but often it could be coming from offsite as well. Maybe it's coming from a neighbor or an industrial plant nearby. And I think we certainly heard a lot in public discourse around odors and community stakeholders around these RNG operations. And I think being able to point out when these emissions are actually coming from offsite, that can be a helpful tool as well. And so you're not getting blamed for that. Okay, so that was the last slide. So I'll just end here. Got my contact information, but as Braxton said, we certainly encourage folks to reach out through the website. We love having conversations about this. I guess I should also say thanks to Kathy. She's been a partner in crime for me in this work, and she knows a lot more than I do about the nitty gritty details as well. And shout out to my colleague Gage as well, who's on the call and has done a lot of the frontline work and visiting these sites and working with operators.